regard to insoluble salts, there is already some cation or anion already present in there. And so actually, instead of 0, but everything else is the same because we have a change in terms of x. That's going to be the same. And we're going to take the initial, apply the change, and come up with equilibrium concentrations. That's going to be the same. So it's going to be very similar, but this is not 0 yet. And so the example I've got is this one. I was trying to think how best to kind of look at this. But lead, let's see, yeah, lead 2 iodide is relatively insoluble, but notice that the first solution we have, it's dissolved. It just means that the molar concentrations raised to the stoichiometric coefficients have not reached the KSP yet. Think of the KSP as a tipping point. Basically, things will be soluble if you multiply them together and it's under that. If you're under the KSP, then it's going to be dissolving. Right, it's undersaturated, exactly. So then all they're saying is they're taking this, in this little dropper bottle over here, is another ionic compound solution of potassium iodide. So they take some potassium iodide, they squirt it in the lead 2 iodide, and the common ion is the iodide. The potassium is a spectator. I think we've talked about spectator ions before. It's just along for the ride. So what happens then is that the molar concentration of the I- increases. So now when you go ahead and plug it in to the molar concentration of lead 2 that was already there, plus the iodide that was there, and then the new iodide, now you have surpassed the KSP, basically. It's the common ion effect. Yep, yep, yep. So we're going to work a problem, and I'm going to suggest using the ice table. I think a few slides from here already has the ice table, so I think I couldn't decide what I want to do.
So you'll be told, I guess, what's already there.
Yes.
Okay.
Yep. But sometimes you're told in different ways. On my, when I work problems, I like to doodle this one, sort of. So, okay. So if you read the italics, what is the molar solubility of calcium carbonate in, it's almost like you're reading double, 0.1 molar calcium nitrate. So here's the deal. Okay, basically, you have, I looked at the common ion already. You have calcium nitrate, it's soluble, really pretty soluble. So in this, instead of pure water, you have, I'll go ahead and do it this way. I'll put CaNO3, okay, you've dissolved it up, and it's broken apart into Ca plus 2AQ and NO3. Oops, must be a 2 there. Thank you. I was like, whoa, that doesn't. 2NO3. There, I'm cool now. I fixed it. Ca quantity NO3 2. It breaks apart into 1 part Ca2 plus and 2 parts NO3 minus. And they say that this was 0.10 molar. So hopefully, we talked about this before. I bet you buy this, that this must be 0.10 molar, and this must be 0.20 molar. Okay, so this is what you have swimming around in here. Now, nitrate, spectator. Now, you'll have to read it, if you're like me, a few times to kind of settle into the problem, because it says, what is the molar solubility of calcium carbonate? That must be your insoluble salt. The equilibrium of interest is calcium carbonate. Okay, insoluble salt. It ionizes to form Ca plus 2AQ sparingly plus CO3 2 minus AQ. Okay, so that's what we got going on here. We could add to our picture, and basically we are going to dump in CaCO3 solid. And the question mark is the molar solubility, or moles per liter, that we can dump in there. That's what the question is. So we said the KSP expression, or the equilibrium constant expression for this, it would be the molar concentration of the calcium plus 2 cation raised to the first power times the molar concentration of the carbonate ion also raised to the first power. Okay. And we have molar solubility of is 5.3 times 10 to the -5th molar. So that means if I go ahead and dissolve 0.5.
Sorry, molar solubility, the 5.3, that's the KSB, so that,
No, that's not the KSP,
That's
that's
not
the
the
molar solubility,
okay, got it.
moles per liter. So yeah, good question. So 5.3 times 10 to the -5th, that will give you 5.3 times 10 to the -5th, 5.3 times 10 to the -5th in pure water. Okay, but it's not pure water. So I was trying to think, like, oh my gosh. I thought this is how this goes. So the KSP is given, and it's 2.8 times 10 to the -9th. Molar solubility, I'll put in pure water. Now, the whole idea of the common ion effect, does this make sense? That the molar solubility should be less. Why? Because there's already some ion in there.
Where did you get the 2.8?
It has to be given to you.
Okay.
Yep, it has to be given to you. So kind of what I said, it's almost like these, you have to find your way oftentimes through multiple ionic compounds to get to what the problem is. And sometimes when I'm grading the exams for this test, that's the problem, is you didn't see through the trees through the forest, or forest through the trees. So we've talked about if we let the molar solubility, this is pure water, pure H2O. If we let the new molar solubility in 0.10 molar calcium nitrate, okay, if we let the new molar solubility be X moles per liter, then it's gonna dissolve, and we're going to get X moles per liter going to dissolve into our solution that's not pure water. Okay, so, all right. Finally, bless you, to the ice table. Let's go ahead and put the cations over here. We'll make the first one, or ions over here. We'll make the first one the cation, molar concentration of the cation. Make the second one the carbonate. Okay, and now finally something's a little bit different than we looked at before. The calcium you have in there, to start with, is 0.10 molar.
And how did you get those molarities?
Those came from the story problem that said
Okay.
that it already had 0.1 molar calcium nitrate. You buy that? So our initial here, nothing. Nope, no carbonate. Okay, change, we're going to go ahead and make this, the molar solubility is X, so the amount of calcium we're going to get is X. The amount of carbonate we're going to get is also X, but be careful, it just so happens that because the way it breaks apart of the stoichiometry is 1 to 1 to 1. So far, very similar. So now we get equilibrium concentrations, and we get 0.10 plus X is at equilibrium our calcium, and then our carbonate is simply X. All right. So what we did before was to take these then and substitute them in to our KSP expression. right? So here's where it's a little bit different than the problems we worked before going to the quadratic equation. There's an important simplifying assumption that you can make with this sort of problem, and I'm expecting you to use it. Okay. So bottom line is we get KSP now is equal to the equilibrium concentration of calcium, which is 0.10 plus X, times the equilibrium concentration of the carbonate, which is X, is equal to the KSP, 2.8 times 10 to the minus 9th. And actually, you know, I told you how acids and bases, that chemistry has a bunch of equilibria, and we do simplifying assumptions there too. So remember, X is supposed to be small. You're like, what was X? That was the molar solubility. Okay, these things are basically insoluble, so it should be pretty small. Do you guys buy this? That if X is significantly smaller compared to 0.10, which it should be, okay, if that's the case, then when you look at this first term, 0.10 plus X, the X is just a blip. And basically that first term boils down to 0.10. It's a beautiful thing. And you get around the quadratic. And actually you can prove to yourself that going this route, making this leap from the quantity 0.10 plus X is essentially equal to 0.10, that works with the amount of significant figures you're allowed. I know. Yay, no quadratic. So let's go ahead and rewrite that KSP expression, and now it simply becomes 0.10 times X, okay, is equal to 2.8 times 10 to the minus 9th. So I can do that one.
Yeah.
Move the decimal place over. Okay, so now you know that X has a value of 2.8 times 10 to the minus 8th. And we defined X as the molar solubility, so units for X will be moles per liter. So now here you can already say, was that reasonable? Did we go out on a limb with this? So is indeed 2.8 times 10 to the minus 8th, is that significantly smaller than 0.10? I'd say yes.
Is it always going to be significantly smaller? Or should we check it?
You should probably check it. Yeah. And the magnitude we have here of, 7 is pretty good. 7 decimal places. Yeah.
So
Because you could only round to 2.
you check it that way, or you check it in the formula like we check the others?
You could
Or we're
You
gonna
could just
test?
check it this way probably, and if it's close, you can kind of wrap it back through.
That's gonna be the
Yeah.
answer.
But this idea of checking a simplifying assumption, actually this lends itself, if you had a chance to look at the calculations, what we're doing tomorrow's lab, there's a different type of simplifying assumption. Or it's similar, but, so you can check it. Okay? All right, I like them. Okay. So, and yeah, your guys' point is well taken, if your molar solubility had been, 0.001 moles per liter, I'm not so sure that was fair. Then you need to go quadratic. Sorry. Which can be done. Okay. Okay, so let's take a look at these. And we aren't going to get to another assignment slide, so this will be the only ones that are due for Friday. But, let's see. When you apply a simplifying assumption in your problem, you have to say where it is that you're applying and what you're assuming. I'll see if these have any. All right. So this is a good one where we're switching it up from calcium carbonate to magnesium hydroxide. Be careful, magnesium hydroxide as it ionizes or dissolves, you get 1 unit of magnesium and 2 units of OH hydroxide. So be careful. So the KSP expression, of course, then looks like that. So let's see what my hints are. That you're supposed to run it in water, and then you're supposed to add the common ion of magnesium, and then you're supposed to add the common ion of hydroxide. So it's very similar to this. You're going to basically run it 3 times. You're going to have 3 molar solubilities. So I went ahead and have a picture for each one. So there's water. There is when you have magnesium. And there's when you have hydroxide. So you might be wondering, Mrs. Snipes, do I really have to do, this stuff down here? No, but it doesn't hurt. What you really need to do is recognize that when you have, for instance, up here, either one, I guess. When you have 0.0862 molar magnesium chloride, your initial concentration of your magnesium ion is also 0.0862 moles per liter. If you do this, you have more of a better chance of catching the whole stoichiometry issue that gets students so bad. So then the initial for A is going to look like this. Okay. Notice for A in water, so no initial, no common ion effect. And for B, it's going to look like this, where you do have a certain amount of magnesium present. So I say use simplifying assumption here. X is your molar solubility. If X is appreciably smaller, significantly smaller than 0.0862, then this thing boils down to 0.0862. So I probably need to see this somewhere. See this green right here that came right before the purple? This is what I mean to say I need to see. And then I went on to say purple. Purple goes to part C, where you have the hydroxide ion is the common ion. This one, let's see. Oh yeah, you don't really have to use your calculator for this one. You just get to eyeball them, I think. Or you probably need to put some sort of pretty equations maybe to show it, I don't know. But basically, calcium carbonate is your insoluble salt of interest. What happens if you have sodium carbonate? What happens if you have hydrochloric acid? What happens if you have sodium bisulfate? Look for the common ion. If there's no common ion, it should have no effect. Oh, yes. Okay. Then there's this one. Again, I have to read it a few times before I get my salts. I get my salts mixed up sometimes. Okay, when it says you have a certain molar, 0.150 molar sodium sulfate, well, I bet that's not your insoluble salt, right? It goes ahead and says it is saturated with silver sulfate. And you're supposed to knock out the KSP value. So this one is a little bit more, I'll kind of give you a path to how you can get this one down. If you recognize that the juice you're trying to dissolve your insoluble salt in is, we have a spectator ion, sodium, but what we really care about is the sulfate. Okay. Notice that what they're saying is it's saturated in silver sulfate, so to me, in my mind, I have silver sulfate down here precipitating at the bottom. Silver sulfate, you can't go wrong writing the equilibrium expression of dissolving this insoluble salt. So here it is, our insoluble salt. Again, don't forget that we get 2 parts of Ag+, so we have to square that in 1 part of SO4. Let's see. Okay, so then back up to here, the problem goes on and says, well, I know that I have swimming around in there silver ion in the 9.7 times 10 negative third molar. So what you can do now is plug in your silver ion that you got from the problem and plug in the molarity of the sulfate that you got from the only source of sulfate is from your sodium sulfate, which is soluble. Plug those back into your KSP expression, and you can get the KSP. So that one isn't as bad as I remembered. So for this one, you have not pure water, but you have sodium sulfate. The volume and molarity is given. And you're going to try to dissolve an insoluble salt, calcium sulfate, and how much of that will go in. So, again, if you do this route, I also like this route. This is dissolving the soluble salt, okay? Notice the one-way arrow. The insoluble salt is the calcium sulfate. So now when I talk about calcium sulfate, it's insoluble. I'm going to go ahead and show the double arrows. Write the KSP expression. Can't go wrong, writing the KSP expression. So I went ahead and wrote my calcium and my sulfate in there floating around, and I want to know what sort of mass would be present floating around in that volume of solution. So we can come up with the molar solubility of calcium sulfate with the common ion of sulfate, just kind of what we've done here. This requires, I'm reading it, I'm like, no, you need to require. So this would require that you look up the KSP value for calcium sulfate. So get that from the literature. Okay, come up with a molar solubility. Oops, oh, come back here. Are you serious? Once you have the molar solubility, then once you have the molar solubility, then you can use the volume, which is 100 mils, and the molar solubility to get to moles of calcium sulfate that must be bouncing around in there, and you're almost done. Once you have the moles, then you can use the molar mass, the periodic table, to knock out grams. Then my other hint up here was in, yeah, I know. That one probably, of that type, wouldn't make it to the exam, but it's a good one. Okay, it's a good one. Very doable. Okay, so I want to do a few slides, no problems, in the next part. Yes, part 6, the last part. It's the last part. So it's kind of looking like Friday. I bet we'll finish parts. Well, Friday we'll probably just get to almost through part 6. And then Monday we'll finish part 6, let our brains rest a little bit. But Wednesday we do need to kind of ease on into Unit 4. But that only puts one lecture day out, kind of out of sequence. And then your Unit 3 exam is Thursday. And I think this one is in the ICN room, I think. I will double check. All right. But this Thursday you have a lab, right? Tomorrow. Okay.
2 months left?
What's that?
2 months left? Less than 2 months left? Like a month left. Wow.
Yeah, like 5 weeks-ish.
Yeah.
Yeah.
Really? Sweet. Not that I haven't enjoyed this.
I gotcha. So I feel like we've already been kind of talking about this, so I didn't feel too bad kind of starting part 6. So this idea, there's different types of chemical reactions. This one, an ion exchange reaction, is where you have 2 ionic compounds and they switch partners. Okay. So it kind of looks like this, where this is color-coded, where your blues are your cations and your reds are your anions, and notice that they switch partners. Quite clever there, I think. So we've been talking about insoluble salts. So basically, if on the product side, if you have an S next to something, that means that that is an insoluble salt. And we say it's insoluble, but remember that even insoluble salts dissolve to a certain extent, as related to their KSP and their KSP expression. So basically what you're going to see is, I'll go back here. Okay, what you're going to see is you're going to see an S next to one of these. So as in, this forms a solid, and that will be your ionic compound of interest. And then I want you to think about, you're going to go ahead and take that, and you're going to say that it only ionizes just a certain small amount, like that. So, and then we could write a KSP expression for that. Okay? All right. That's kind of how it works. Or that's how this sort of problem works. So I have these videos, I think.
Wasn't our last lab an exchange? Weren't there some
Yes.
exchange reactions?
Yep. I know at the very end there with the silver chloride was okay. Indeed. Okay, so let's see if you can kind of catch the exchange. So this isn't an equilibrium. Sometimes I have students kind of mix, at this point. This is just a one-way arrow. Okay, we have two things that are soluble, just like you saw in the video, forming something that's soluble and something that's insoluble. And like I said, what we're going to take off on Friday is to basically take this guy and go ahead and do some calculations with him. So that's that one. And this is the second one we saw. Two insoluble things forming something insoluble and something soluble. And I haven't had a student ask this, but I bet you guys have great questions. So what happens if you have two insoluble things? I guess it could happen. Don't know if I have to think about that. Okay. So now not videos, but we have some kind of still images of some more exchange reactions where you get a solid precipitate. So that yellow solid precipitate must be lead 2 chromate. The black precipitate, creepy black precipitate, lead 2 sulfide. I just think it's neat where you take two things that are colorless, you mix them together, and you get a... see, is this one that we did? Or maybe in part. The iron 3 chloride in presence of a hydroxide ion forms this iron 3 hydroxide.
Looks familiar.
It does to me
The name
too.
looks familiar.
Yeah. The tan, it was like we were stressing the equilibria, and this is one way we stressed it. Because the other, it was the thiocyanate and iron 3 makes that blood red complex.
Not the whole thing, Marie.
Did you find it in there?
Mm-hmm. Yeah, it was iron and the thiocyanate.
Yep.
Not.
But this was a way to remove the iron and to push it the other direction, I think. Okay, this one's pretty. The precipitate silver chromate. Exchange reactions to get a precipitate actually are ways at times of cleaning up water, if you want to remove something. Okay. So like I was saying, you look on the product side, it's the thing with an S that you're going to run with, okay? And sometimes for your exam, for this material, I will expect to see the exchange reaction for the balanced process, and also then, of course, the KSP expression, or the equilibrium and then KSP expression. So kind of think along those lines. I was talking to my mom about insoluble salts on the way to school today, and she was like, "That's so cool." Except I just use plain salt, like or sugar. I said if you put sugar in water, you know, there's gonna come a point where you just put too much sugar in and get that stuff down the bottom. And she thought it was really cool where it goes back and forth between, and she called it crystallizing or solidifying, you know, and being in solution. She's like, oh, that's so cool. I'm like, yeah, it is, because it has a constant amount. Okay, so there's my little note for Friday. And actually, this was from last year, so I'm still Friday.
Oh, wow.
I know. So that's how far I wanted to get today, and to
Skills.
start the problem Friday.